Professor Stelios, I'd love for you to take over. But before you begin, if you could introduce a little bit about yourself and the work that you're doing, in Patras, I think that will be helpful to set the context. Over to you.
Yes, I will say also this in my presentation, but in any case, my name is Stelios Neophytidis or Stylianos Neophytidis. Uh, so I'm a research director at the Institute of Chemical Engineering Sciences in Patras, Greece, and where I have been working on electrochemical science and technology, mainly focusing on fuel cells, water electrolysis for the last almost 30 years. So I will be glad also to share my knowledge and our achievements with you today. And maybe I can proceed with sharing my screen or whatever. What I'm going to discuss with you and present is how we can imagine the development of sustainable energy technologies. So I will focus my presentation on high temperature PEM fuel cells, which is one of our proprietary technologies, and discuss a few applications for them. So, as I have told you, I'm a research director at the Institute of Chemical Engineering Sciences. This is a research institute, a governmental research institute that is situated in the North Peloponnese, as you can see here. In any case, what I was saying is that I'm a research director at the Institute of Chemical Engineering Sciences. This is situated in the North Peloponnese in Patras. You can see a view of the research institute. And the institute is mainly focusing its activities on energy technologies, on environmental studies and technologies, and also on physical chemistry and material sciences. So, what I would like to say, will say a few things about the sustainability of using energy systems. So the vision that the societies and what we have in our mind is mainly to be able to use renewable energy systems in an uninterrupted way to produce electricity the way, considering that the renewable energy systems are intermittent, the way that it is possible to have continuously electricity and in general energy from renewable energies is mainly to be able to store hydrogen, to produce hydrogen with these systems and store the hydrogen, and then use hydrogen at will to produce electricity and most probably also heat. So, as you know, this is a very clean technology, as the only effluent gas that is being produced is water. So this by recycling water, we are just closing the cycle, and we may have this sustainable system by using the renewable energy that is coming to the planet. So the idea is initially to produce hydrogen. How we produce hydrogen? The hydrogen is mainly produced, and when we're discussing about green hydrogen, is mainly based on water electrolysis. So we get renewables and we are electrolyzing water to produce hydrogen and oxygen. Hydrogen is mainly stored, which is used afterwards with any technology, any fuel cell technology to produce electricity just to feed and provide electricity to any kind of needs that our modern societies need. So I will focus mainly our discussion on the fuel cell technology that we have developed. and discuss a few applications based on this technology, because as you know, there are different types of technologies, of fuel cell technologies, based mainly on the materials and the ionic transport that each technology is using. So this technology has been developed the last 20 years. It is a proprietary technology, and the investment on this and the research projects that were activated to do this, they estimate over 20 million euros. So we have a vertical know-how, and as you can see, we have activities and knowledge on the development of new catalysts, polymer membranes, polymer electrolytes, electrodes and membrane electrode assemblies, engineering and designing and engineering of the electrochemical reactors, and the balance of plant that is needed to put all this technology into operation. So you can see a real view of what we are producing here. On the left side, it is the so-called high temperature PEM fuel cell. This is an example of a 2 kilowatt fuel cell. We are developing also high pressure PEM electrolysis, approaching 100 bars. All these activities, the last 10 years, have been developed and financed also by the European Space Agency, as you can see, and you can see the balance of plant just to incorporate these two and work and produce electricity, produce hydrogen, and also electricity from the renewables. So I would like at this point just to mention also my colleague, Professor Ioannis Kalitsis, who is a professor at the University of Patras. He's a polymer scientist, and we have done together with his group all these developments that I'm going to show to you. So what is a fuel cell? Here you can see a representative video that is showing also the electrochemical process. So the materials that are being used is we have initially the proton exchange membrane, which is the proton conductor, is a solid state electrolyte. And this is sandwiched between the two electrodes. The electrodes contain these are conductive, and they contain the so-called electrocatalyst, on which the two half reactions, the anodic reaction and the cathodic reaction, takes place. So this assembly should be like this in order to be able to have the oxidation of hydrogen on the anode into protons and electrons, and the reduction of oxygen at the cathode into water into water by reacting the oxygen with the protons and the electrons. With this setup, it is possible just to isolate and take the electrons of the reaction into an external circuit, and in this way we can produce the electricity that's needed. So overall, we are just transforming a thermal reaction into an electrochemical reaction, and exploiting, instead of producing heat, we are just producing electricity, which is the best way, the highest grade of energy that we can use in the universe. So, what are the materials that we are producing? It is the polymer electrolyte membrane. You can see an example of it, and also the nanostructured electrocatalyst. These are electrocatalysts bearing very small amount of platinum, and it is we have the nanoparticles of platinum deposited on carbon nanotubes. These two are formulated into the so-called membrane electrode assembly, which is the heart of the electrochemical system. Here you can see in reality on real dimensions, not experimental. So we have this is the membrane on the left side, which is it has an area of 200 square centimeters, and this is sandwiched between the two electrodes. So the black thing that you see here, it is the membrane electrode assembly. It is the electrode that is being attached with platinum-based catalyst, which is attached on the membrane. And below here, it is the design of the bipolar plane, which is made just to connect the membrane electrode assemblies in series and also to provide the gas distribution over the entire surface of the MEA. So in this, at this point of our development, we are able to produce reactors with efficiency of about 50%. They are operating at high temperature at 200 degrees. So the polymers that we are producing, they are able to operate at 200 degrees. And why this is significant? Because in this way, you can manipulate and manage the heat production of the system in a more efficient way. The higher the temperature difference of the reactor with the environment, the smaller is the cooling system that you have to develop in order to cool down the reactor. As we will see, this is very privileged, especially when we have to use air-cooled systems and have a very simple and lightweight balance of plant, as we will see further on when we were discussing the applications for aircrafts or unmanned aerial vehicles. So at this moment, we are operating with a power density of around 0.5 kilowatt per kilo. And the next one, it is our vision how we want to reach the efficiency of the system in the next years to reach about 60%, increase a little bit the temperature, so that we will be in the range of also conducting catalytic reactions on the electrodes and operating with a power density of more than 1 kilowatt per kilogram. It is very essential to notice that we give special attention on the power density because with this technology, we are just discussing, considering also our European Space Agency applications, the to develop a lightweight system for space or for aviation. It is a must for the application of these systems in aircrafts or in the space. So I will enter and discuss a little bit on the applications. I will start with the unmanned aerial vehicles or small aircrafts. This technology, it is quite interesting for this. This is an example of the fuel cell that we have created in collaboration with the European Space Agency. And for the time being, we are working on this for the development of system for life support or for lunar application. On the right side, you can see the characteristics of the system and of the reactor, and you can see it is possible at the very end to operate at efficiency of around 55% and power density of around 0.6 watts per square centimeter. This is the system that we have in mind for the applications for regarding the UAVs and the general the aviation. So this is a very simple balance of plant. You have only the fuel cell, which is air cooled, so you will not need any voluminous heat exchangers to cool down the stack. You can have hydrogen and oxygen either in high pressure or in liquid form. It is something that it is under discussion in the case of aviation. And what you have to do is to control the flow that is entering into the system. So we have a very simple balance of plant. We can supply the gases in a pressurized form. The fuel cell, due to the fact that it's operating at this high temperature, it is very easy to cool it down by just blowing air on the fuel cell. And the fuel cell, it is can be heated very fast and reach 100 degrees, which is the the starting operating temperature of the fuel cell in 5 minutes. And the heating up process is done electrically, utilizing a very small battery to do so. And the fuel cell, as we said, is air cooled and is using, and we are proposing the use also of oxygen tank instead of incorporating voluminous air blowers that will add additional weight to the system. So the resulting benefits by the use of this high temperature PEM fuel cells is the high operating temperature of the fuel cell can allow the fuel cell to be very simple, which means that it is cooled down with air. The feeding gases are not humidified, and I can compare this technology with the low temperature PEM technology that it needs humidified gases. So you need another one peripheral, which has additional weight to introduce. And so this makes, as we saw, the balance of plant quite simple. The feeding gases can be introduced into the stack at even at very low temperatures, even below zero. So there is no reason to develop systems to heat up the gases. And the cooling effect of the oxygen and hydrogen entering into the reactor, it is very minimal. So we estimate, and we also measure, less than 10% of the heat that is being produced by the fuel cell is needed to heat up the gases. So the stack can easily afford the operation at higher operating pressure. It can operate at 3 or 4 bars. And this is something that it is already proven. And we can achieve right now for the fuel cell power densities of 0.5 watts per square meters. If you put the fuel cell together into a system, then the power density of the system is around 1 kilowatt per kilogram, which makes this system quite competitive to the conventional internal combustion engines system that they are using in the aviation. The other thing that we have to mention, especially when we're discussing about UAVs, it is estimated that the flight by using fuel cells and pressurized or liquid hydrogen, this can be doubled, and we can achieve longer flights as compared to the batteries that they are using right now for the UAVs. Another application is, I will go faster in this, is the use of these high temperature fuel cells for stationary and industrial applications. Why I'm focusing on this? Because of the high pressure, of the high temperature, operating temperature of the fuel cell, we can produce superheated pressurized steam, which can be used for several applications. I can give one example here. So this pressurized steam can reach pressures up to 10 or 12 bars, and this can be even useful just to operate a steam turbine and increase the efficiency in electricity production. This is achieved because we have developed a closed loop for the cooling down of the stack. And in this way, we are just cooling down the stack by using a two-phase water steam flow through the fuel cell, and so that the coolant, which is mainly water, is operating continuously at the operating temperature of the fuel cell. So the fuel cell is being cooled down by just removing the heat from the fuel cell by evaporating water and having a two-phase equilibrium within the stack to cool the stack down. In this way, we are able to come out with a steam which is at high pressure and high temperature, and can be used for several applications. One application is mainly to produce electricity from natural gas, and in this way we are able to increase the efficiency of the system by just utilizing the heat that is being produced by the fuel cell. So you can see that we are, in this case, by when the fuel cell is producing about 1,100 watts at 180 degrees Celsius, about 440 watts can be used to create steam, and which can be used in the steam reforming reaction of the LPG or the natural gas. In this way, we can use and utilize this heat just to keep and have a high systems efficiency. Otherwise, if this will not be done, the systems efficiency can be as low as 35%, which means that we are losing a significant part of electricity. Instead of getting electricity, we're mainly producing heat. So in this way, this is an example, and in this way, in the industrial applications, we can have several examples of using this high temperature and high pressure steam for various industrial chemical processes. But this is how the system that I described before is operating. And what we are doing is that the reformate This is the performance of the fuel cell with the reformate that is being produced by the reformer. And because of this high temperature, there is no reason to clean up completely the reformate from carbon monoxide, as it is the case with the low temperature PEM fuel cells. And you can see that the performance of the fuel cell is more or less similar to the performance of the fuel cell with feeding the fuel cell with 100% hydrogen. I will say a few things on high pressure PEM electrolysis in order just to introduce you also into the regenerative fuel cell approach. With the water electrolysis, it is possible to split water, as you can see here, by using renewables into hydrogen and oxygen. And beyond this, it is possible with the PEM electrolyzers when using a polymeric membrane as a proton conductor, as you can see here. We are able to pressurize hydrogen and oxygen at very high pressures. At this moment, we managed to do it up to 100 bars in 1 kilowatt electrolyzer. And in this way, we are able to avoid the voluminous and low efficiency hydrogen compressors. So the system and the electrolyzer is operating both as a water splitting machine and also as a pressurizing machine, as a compressor for the hydrogen storage in high pressure. So this is an example of the reactor that we have produced for the European Space Agency with specifications to be able to be lightweight again, to operate at very high efficiency, close to 85 to 90%, because we do not want to lose and produce enough heat from the system. And this was done within the framework and our collaboration with the European Space Agency. This is where we are now. We are operating at this high pressure with 82 to 85% efficiency, and aiming with the appropriate development of electrocatalysts and the engineering of the system to approach 200 bars at 90%. This is the last application that I want to discuss, and this is the regenerative fuel cell system. This is a system that can provide sustainable and uninterrupted renewable electricity and heat production. So what is this about? This is a system that is combining the electrolyzer, a PEM electrolyzer, that is getting electricity from renewables, is splitting water. Hydrogen is being stored either into metal hydrides or into high pressure vessels. And this is being used at will to produce electricity when it is night or when the sun or the renewables are not available. So the fuel cell, the high temperature PEM fuel cell, is able to provide the electricity and also the heat for the residences, if we are discussing about residential application. And the produced water is then is returned back to the electrolyzer. So we are not spending any water in this case. This is a closed water loop, and 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 you can see and consider it as a black box, which takes solar power or wind power, is storing hydrogen, and the outlet of the system is mainly the electricity production, and also is covering the needs of the heat of the constructions and the houses and all this kind of stuff. With this, I would like to add my presentation, and I'm willing, and we will be happy to discuss with you and answer any questions that you may have. Thank you very much.
Well, thanks very much, Professor. If I can bring in our panel of experts, Santhosh, Georgios, if you're around as well, please. We heard you speak about quite a few innovations, and you also brought about some of the applications that could have been new for several people here in the audience, Professor. If you could tell me what was the biggest innovation that you've made in your fuel cell, right? That is giving it more versatility and flexibility.
This is mainly, we started with the development of new polymer electrolytes. So the polymer material that we are using as a proton conductor, this defined the technology, and mainly the operating temperature of the technology. It is very good to operate at this very high temperature, and I don't think that there are other materials than the material that we have developed to operate at this high temperature approaching 200 degrees. This technology operates with another material, the so-called polybenzimidazole, at higher temperature, but it is around 40 degrees lower than the temperature that we are operating.
Wonderful, Doctor. The other thing is, if I can ask Georgios this question. Georgios, are you available?
You hear me? I'm here.
Yeah, wonderful. Georgios, what is, I know you've worked with Professor, and you've seen what Professor is talking about. So if I could ask you one question, what is one of the biggest advantages of having, the hydrogen produced at, 100 bar or 50 bar?
Well, it really depends on the application, but if you see the golden standard of what today of how hydrogen is produced today through electrolysis is that we have two kinds of system. The one is this pressureless, so it's basically on atmospheric pressure, which needs very intense amounts of energy to be compressed down to a useful pressure, or a useful volume where you have good energy density of the fuel. And the other one is around 30 bars, let's say, and 30 bars is a pressure where you start to be spending a lot of less energy than that. Nonetheless, you have a very complex system of compressors. Hydrogen compressors are complex machines that need a lot of care so they can operate properly. I think producing hydrogen at these high pressures is enabling the elimination of, or let's say enabling the simplification of systems, especially on hydrogen storage. And this is a benefit for the cost of such applications of hydrogen production. The second point is the downstream processes. So usually when you see projects, especially at large scale, is that you have downstream processes like methanation or like ammonia production and so on that require a certain quality of the feedstock, of the hydrogen feedstock in the as an input. And not only that, the conditions where the reactions are happening for producing methane or ammonia are given. Methane is not so critical, but ammonia usually requires hydrogen at higher pressure. If I'm not mistaken, it should be around 70 bars. So you can have you can basically eliminate compressors on the side between your electrolyzer and your buffer storage in such a streamlined process where you have hydrogen production, methane, and then ammonia production, for example. And this can simplify or can reduce the cost of the balance of plant for such applications significantly.
Oh, that's great. Thanks very much, Georgios. Santhosh, I know you understand all of this much better than I do, and I'll be honest about this. So, from what you heard, from what Professor spoke about, and what Georgios has been telling us, where do you think there's been some real innovation, and if there were any lessons you take from this, what are they?
No, thanks. First of all, thanks, Nish, and thanks, Professor, for let's say explaining the work you've been doing. We work primarily in the low temperature PEM fuel cells, which I'll talk about later. But I think HT-PEM has been always, the bridge between the ultimate SOFC and your LT-PEM, right? And one of the things which we have seen, for example, HT-PEM going to be applied more and more is in these aviation applications, both for these small scale aviation, but also for these regional jets, where neither an SOFC or a LT-PEM can do the job. So I think that is a really good application, and I think the high power densities which you showed is going to be very important, right? I mean, considering the lightweight of the aircraft. So I think that is something which was definitely a takeaway from me to understand, that there is progress there. And we know in Europe, right? I mean, in fact, like companies like Zero Avia, or in fact even some other companies have been developing their HT-PEM fuel cells, but it's one of the areas of continuous development. So thanks for sharing that. So perhaps one question or as a follow-up to that as well, maybe a couple, perhaps you could answer. One of them being like in terms of lifetime of these systems, right? I would imagine that considering these systems are just being coming out and being developed, we would not have significant data regarding degradation at high temperatures. So what is your prediction on those, and what is the outlook of that? I would put it this way. The second question I'll also ask, and you may answer both in whatever order, sir. Second question being that let's say these are higher temperature systems, so they do require startup times. And I did see in one of your slides somewhere that you could have a fast startup time, both either electrically, thermally, or using a battery. But always the initial, let's say the parasitic load which you need to start it up is something which is not available always, right? So then you'll have to put in expensive batteries to or load life cycle batteries to kind of start them up. So how do you see that? Do you see that as a bottleneck, or how do you see solving for that? I mean, because it's high temperature, right? You could be also potentially storing that in some kind of a PCM or a thermal storage and use it back again whenever you start up. So have you considered those kind of let's say integrations as well?
Okay, I see. The first question is, what about the longevity of the materials at these very high temperatures? Yes, this is true. We have developed quite recently the most difficult problem is the polymer structure to withstand these high temperatures. Also, because this technology needs also phosphoric acid that is being imbibed into the polymers. In some cases, you are losing at this high temperature some of the phosphoric acid. But in any case, we were very happy because quite recently we have long-term stability tests and startup test of such a system with new membranes, this is a new type of membranes that we have developed. It is two-layer membranes with different materials. and they can reach at different doping levels in phosphoric acid. In any case, it turns out to have very good results operating at 200 degrees Celsius and at 4 bars. And also with pure hydrogen, we have seen for about 1 month operation a very small degradation. I did not include this in my slides, but this is the case. I think this is a quite nice outcome, and also it seems that the operation at high pressure is promoting the operation of the fuel cell in considering several. It's not only that it promotes the kinetics of the reduction reaction of the oxygen, but also it promotes also the conductivity of the proton exchange membranes. This is one thing. I think we are in a good way operating towards these directions, and I hope that the long-term stability will not be a problem. Regarding the heating up process, look, this technology will start operating at 100 degrees above 100 degrees Celsius. We avoid to operate lower because the produced water will be condensed, and this will remove the phosphoric acid from the membranes. So the limit is just to operate above 100 degrees. Start operating above 100 degrees and let the system afterwards to increase temperature autothermally. And this is the case. For this, you need a very small amount of energy to reach this temperature. So if you use a battery, this battery will be a small battery with small capacity, and this will not be a burden on the system, on the balance of plant of the system. It is just for starting up, and then this battery again can be recharged by the fuel cell. I don't think that this is a problem. And if you compare this with the solid oxide fuel cell, for example, which needs some hours to be heated up, to do this in 5 minutes is not a problem.
Got it. Thank you, Professor.
Wonderful. So, Professor, we'd love it if you could just stay on. We'll have a question and answer session in about 15-20 minutes. In the meantime, let me introduce Santhosh. Most of you all might know Santhosh. You know, he's been a very vocal person in the green hydrogen sector here in India. So Santhosh has spent quite a lot of time working in Europe. He's been in hydrogen, oil and gas, and he finished his studies at TUV Delft, right?
Not V, but TU, yes.
Okay. But anyway, Santhosh, I'll pass it on to you. Why don't you say a few words about yourself, and then over to you.
Sure. Let me just quickly share my screen as well. Give me a second. Get started.
And the rest of them, the audience, if you have any questions, just put it into the chat box. We'll try and interrupt these people whenever we could and ask them questions. But we will have an open flow session at the last 5-10 minutes, so you can ask your questions on the mic if you think it's too complicated to put it in. Well, we see Santhosh's screen here.
Wonderful.
Let Santhosh begin.
So basically, a very quick introduction. My name is Santhosh. I'm the co-founder of H2 Carbon Zero and Umagine. So working in the hydrogen space for a pretty long time. In fact, straight from let's say out of my college back in the Netherlands. I worked with Shell for a number of years, and then after a couple of consulting stints with McKinsey, started started my own company back in 2019. So the past 5 years, we have been, let's say, actively working in hydrogen. I'd say 2.5 years first in the Netherlands, and then over the last 2.5 years based out of India. We primarily work on hydrogen fuel cells for stationary power applications, low temperature. But in addition to that, we have been also active in the ecosystem development space in India, where we have been also working with policy aspects as well as strategy and EPC projects in India in the space of green hydrogen. So green hydrogen is all we do. That's our bread and butter, just like for Nish and Professor for perhaps, but very few of us are like that. So I mean, I'll skip the hydrogen bit, but I mean, I'll just tell a couple of things over here. So whatever large hydrogen production comes up, right, application needs to happen, right? So without the demand side, things are not going to work out. And we do see demand there, obviously, in the current industrial scale when it comes to refinery and fertilizers. But these are also the most saturated or most commoditized markets when it comes to kind of getting in hydrogen and having a bankable use case without constant subsidies. And therefore, we strongly believe in use cases where green hydrogen makes sense, right? Makes a business case even today. So those are applications using fuel cells, in fact, in certain heavy transportation applications, in certain kind of aviation applications, and primarily in stationary power energy storage applications, right? So so beyond the global kind of movement, obviously everybody knows about the National Green Hydrogen Mission. There's a lot of work happening over there, but one part which people don't know much about is that the power sector aspect of it is pretty solid. I mean, there was an announcement by the power minister last year that let's say they are looking at green hydrogen for the long duration energy storage applications rather than battery energy storage systems. So we are talking about 6-8+ hour of energy storage, where about 100 megawatt of projects are going to come up in the next couple of years with some viability gap funding. So that's very interesting. But in order to support that, there are a number of power sector PSUs who have taken the lead with hydrogen-based microgrids, right, which has a solar electrolyzer, hydrogen storage, and a hydrogen fuel cell. And these are some of the projects what you see here, NTPC and HPC, and we have been involved in all of them in one capacity or the other. In SJVN, we have delivered our fuel cell. In NTPC, we're going to deliver our fuel cell. Project is under execution. So these are all small scale projects currently, but then what you see is that these are like test projects which will then expand to larger scale, megawatt scale fuel cell projects. And that's something is already happening. There's a 200 kilowatt tender already going to be awarded by NTPC, another 200 kilowatt coming up, a megawatt fuel cell tender coming up. So a lot of action, I'd say, pioneered by the public sector in India. For those uninitiated, fuel cells have been around in the market for a very long time. In fact, you see some of the companies like Amazon's and Microsoft's and Walmart's already using fuel cells, not our fuel cells, but then let's say specifically in the US, you have companies of the likes of Plug Powers and Ballard and Bloom Energy delivering and having a very strong presence, close to $1 billion plus revenue of each of them in the stationary power market. And why hydrogen for energy storage basically comes down to this chart, right? I mean, and this is basically not our analysis of IEA. Our analysis comes in the next slide. But let's say for very short duration of energy storage, which we define as, let's say, less than 1 hour or 2 hour, we expect battery to be the predominant solution. But then according to IEA, anything beyond half a day or longer, right? Hydrogen is the only solution which is there across various use cases. And there's a gray area in between, which is a bit geography dependent, but this is like the fundamentals of, let's say, why hydrogen energy storage and hydrogen-based fuel cells make sense. Let's say, again, this is perhaps not that interesting to many, but the market size for fuel cells is actually quite big because it's anything to do with power generation. There's a lot of different applications across prime power, backup power, and material handling. But then let's say the market which is currently serviceable is fairly limited. That's because of the let's say the high cost of electricity from the fuel cells and hydrogen. But as it goes down over the next few years, we expect the market to kind of ramp up and be one of the drivers for green hydrogen economy overall. I mean, that's what we expect going forward. Now, when we talk about stationary, I mean, so hydrogen fuel cells have a number of different applications, right? So already Professor talked about some, but there are portable applications like 100 watt, 50 watt kind of applications. There are mobility applications. Specifically, you have trucks, cars, buses, etc. Then you have aviation, right? You have shipping, maritime, so an entire range. So we do not do as H2 Carbon Zero, we do not do all of that. We do focus completely on stationary power use cases. So that's what you see over here across various kind of applications. Anything. So what we see right now is that when you compare all these technologies across levelized cost of electricity, anything above 6 hours, fuel cells are the cheapest, right? And not a lot of people kind of realize it, but actually hydrogen fuel cells based on green hydrogen has the least LCOE even compared to diesel gensets for long duration even today. And this 6 hours is going to go to at least 3 to 4 hours in the next few years. And that's when, let's say, that's when it will be complementary with batteries, which will be great for short duration, right? So this is an installation which we did in, let's say, in Shimla, near Shimla, about 4 hours from there, for a hydrogen microgrid, a 25 kilowatt fuel cell, which is our first commercial deployment. Kind of got ourselves kickstarted earlier this year, where we worked very closely with, let's say, one of our partners who delivered the electrolyzer over there as well. So happy that this is work. This is something which has been commissioned, started up, and we have a use case to demonstrate. Basically, a hydrogen fuel cell, I think, Professor already mentioned about it, but then beyond the core fuel cell stack, right, there are a lot of different things, right, in a hydrogen fuel cell. So to those who are, let's say, new to fuel cells, very quickly, hydrogen fuel cells are very much comparable to diesel gensets, but not to batteries. Why? Because the fuel cell is the genset, of course, in a very different philosophy, but you have hydrogen as the fuel source, right? So that's what would produce electricity. So we have developed our fuel cell, and in which all these systems around whatever you see here, including the stack, is developed in-house, completely bottoms up. And that is where we believe, we believe that the fuel cell stack technology is is pretty mature. In fact, there is still a lot to be done, just like Professor was mentioning, but a lot of work has already happened. But at a system level, we believe the overall, in the end of the day, the customer is going to buy the entire fuel cell system, right? Not only the stack. So, and stack only contributes about 30% of the cost. So we have kind of demonstrated and worked on all these systems to achieve our designs. Currently, I mean, this is a very important number. Currently, if you go and buy a fuel cell for 100, 200 kilowatt range, you're going to pay about $1,500 per kilowatt, $2,000 per kilowatt. So our target is to decrease it by almost 1/3 or 1/4 in the next couple of years by indigenizing almost 95, 98% of all the subcomponents. Anyway, the entire design and engineering is ours, of course, but then by moving towards a maximum indigenization, utilizing the Indian supply chain ecosystem, we strongly believe that these numbers can be achieved. And if these numbers are achieved, then I mean there is no space, there's no place for diesel gensets in the market anymore. So yeah, that's a very quick brief of what we are doing and what is it about. So happy to take any questions. Ornish, over to you.
Thanks, Santhosh. I think that was. Thanks for breaking it down for people who don't really speak the language. It was quite fascinating to see quite a lot of things in your presentation, but we're already getting questions about the feasibility of what's the levelized cost of energy today for a fuel cell backup, right? Do you have a straight answer? Because I know I've been exploring this. People do tell it is cheaper, but then how do you set it up and how do you deliver the project?
So see, everything depends on the kind of application, right? Let's say that when we say a typical comparison for, let's say, 200 kilowatt fuel cell, which has to operate for 8 hours a day, right? 8 hours of backup. Then the cost of electricity from hydrogen fuel cell, again, it's in rupees, so I'll need to convert into dollars. Perhaps Nish, you can help it very quickly. But then in rupees, it's about close to 35 rupees per unit per kilowatt hour, right? Compared to a battery, compared to a diesel, which is more close to 40, and compared to a battery, which is more close to 45, right? I mean, talking about an 8-hour storage. Now, that is considering the current prices of hydrogen and hydrogen fuel cells. Now, as this hydrogen price decreases, let's say to a 200, 250 rupees per kg, I mean, which is of course everybody's targets, and that's why all these $250 billion of subsidies are for. I mean, we are talking about cost of electricity from fuel cells to be less than, let's say, 15 rupees, 12 rupees, or even 10 rupees per unit, right? So when you then do a levelized cost together with hybrid solar wind, then the RTC is going to be like pretty cheap and pretty affordable. I mean, where fuel cell can act as a firm power and solar and wind as an intermittent power. So that's the numbers which we are kind of looking at right now and in the future as we go ahead.
So, in the price is only going down in the future, and you think applications for stationary power usage will only increase?
Yeah, I mean, so see again, right? Let's say there's always a comparison. Right? I mean, currently there are still applications of diesel gensets where the grid is not there, right? But there will be more and more electrification happening, so perhaps those applications will evaporate. But ultimately, you are looking at a high RE penetrated grid with amount of storage, where let's say a hybrid solution of capacitors, batteries, and fuel cells is going together with solar and wind is going to define how the grid is going to be. And of course, there's always space for some other storage technologies like, let's say, pumped hydro or let's say vanadium flow batteries. But again, from a scalability angle, we believe this is going to be the base case with others kind of adding and subtracting here and there. And again, we do not see fuel cell to be a big use case for, let's say, 10 kilowatt or 15 kilowatt application kind of solutions, because yeah, I mean, purely because of the techno-economics, we believe that 100 200 kilowatt and above is where things starts to get very interesting. Yeah.
Thanks, Santhosh. Kalpana, you have your hand up. Since you have your hand up, I'll bring you in, and if you want to, ask your question through the mic, you can unmute yourself and ask. Okay, I'm not sure if Kalpana is there or she has her hand unintentionally raised. But Prashant?
Hello.
Yes.
I'm audible.
Yes, we hear you, Prashant. Please go ahead.
I have a question from the professor, Professor Stylianos.
Yeah, he's here. Please, he
Yes.
hears you. Please go ahead.
Okay. Actually, I am also working in the membrane department from CSIR, CSMCRI, Bhavnagar, Gujarat, and I am developing the polybenzoimidazole membrane. But what I have, we don't have the facilities to perform the high temperature fuel cell. So, and which type of membrane are you using in fuel cell, high temperature fuel cell?
Our membrane is based on aromatic polyethers that they bear pyridine units. These pyridine units, they are able, like the benzimidazole, to be combined and absorb phosphoric acid. And what is the special thing about this material is that it has much better mechanical integrity and can operate at even higher temperatures compared to the polybenzimidazole. So in this way, this is why we are able to operate with these materials, and in some cases combining also PBI, but I cannot say more things about this because it is under protection right now. We are writing a patent, and this makes them possible to operate at these high temperatures.
Because our group also you prepare the membranes for different electrochemical energy devices, fuel cell, battery, electrolyzer, and this institute is basically developing the electromembrane process, electromembrane division, which develops these membranes. So I am working on the polybenzimidazole membrane last 1 year, and I produced some I prepared some membrane. So can we send you a membrane? Then you will test what is the size of the membrane you required and other things. If you can collaborate with us.
You mean to just send us a membrane and do the testing of your material?
Yes, if possible.
Okay. The size that we are using is something like 100 square meters right now. Okay, we can start also with very small sizes,
Okay.
but in any case, the smallest size is the 2 by 2 square centimeters. You have
Sorry.
to know that, yes.
What size?
Two,
What is
two
the
by
size? Pardon, please.
4 square centimeters, the smallest
Okay.
size, which is for the experimental setups. But normally, just to be sure and that this data can be transferred to a fuel cell stack. The best area to test these materials is at around 100 square centimeters.
Okay.
Professor, thanks.
Actually,
Prashant, we'll connect you with the professor. We'll continue with the session until then. Yes, Kalpana, go ahead.
Yeah, am I audible?
Yes, we hear
Yes.
you, Kalpana. Please ask your question.
Yeah, actually, my question may be out of the topic. I actually work on this green hydrogen production by methane cracking. So I'm just worried, like electrolysis, what all you're talking about, that produces only hydrogen in millimoles, or like it is very less, right? So is it feasible?
Well, you were right in how you started this question. But Santhosh, do you want to take this?
See, again, it depends on how much electricity you put in, right? So again, yeah, I mean, the methane as a carrier for hydrogen has more molecules compared to water as a carrier, right? That's a fact. I cannot change that. But then if you look at in terms of let's say a couple of things, right? I mean, one, if you look at in terms of the kind of projects which are coming up currently and all the subsidies, 95% of them or 85% of them globally are for primarily electrolysis as an application, as a use production methodology, not for other applications. There is some where you can do carbon capture with methane. The third thing is that methane, the question is always on, in the end, it's a fossil. And let's say there are questions around, let's say, losses or what do you call it, upstream losses of methane across the value chain. And that is something which prevents a lot of people from classifying or considering methane seriously as a way to produce hydrogen. I mean, which is already, that's what is being done right now, right? 100 million tons, out of which at least 70 million tons, except for China, methane is what you use, right? So, so of course, I mean, methane cracking, pyrolysis, even SMR with CCS or ATR, all those technologies would be more energy efficient and more better on a per unit or a per let's say energetic efficiency basis. But where the world is moving right now is fortunately or unfortunately far more towards electrolysis than anything else. I mean, which I do endorse as well personally, given let's say we are completely dependent on sources which are renewable energy.
Okay, thank you.
Thanks, Kalpana. I think we'll move on to our next speaker before we have a larger open floor session. Vamsi, are you there, Vamsi? Vamsi is another innovator
Yes,
who's
yes,
also
yes, I'm here.
yeah, okay,
Yeah.
fantastic. Vamsi, would you like to explain a little bit about what you've been doing in the PEM fuel cells area?
Okay. So we are a startup company from Hyderabad, Viriya Green Energy Systems. So basically, currently we are doing a 5 kilowatt fuel cell stack currently, but we also have an funded projects from Indian Oil Corporation to develop an LCV, light commercial vehicle. And also we have a funded project from BHL R&D for developing of gaskets and bipolar plates, which we only do for ourselves. Not only for ourselves, we also do the commercial sales for bipolar plates and gaskets. Currently, for the polymer membrane, for PEM membrane, currently we are importing the membrane, but we have a funded project again here, where with the Central University of Hyderabad to develop the membrane part with polymer chemistry, where chemistry subjects related things will done by polymer chemistry group and engineering knowledge will be given by us. So 80% of the fuel cell which we are doing, currently we are only doing 5 kilowatt, and we also have a dedicated agreement with generator company from Europe to develop some fuel cell generator of 12 kilowatt, which we are finalizing, and we'll be doing the first demonstration on August 31st.
All right, wonderful. Vamsi, do you have a presentation that you wanted to share on, on the stuff that you're working on?
Yes, it's a generalized presentation. How should I share?
You should be able to share on, on the top of your screen to the right hand side. You'll see a share
Yes.
button.
Let's share it.
And Vamsi, if you're okay with switching on your camera, I think people would love to see how you look like.
Yeah.
Thanks.
Yes.
Okay, great. Okay.
Share content.
So,
Okay.
Vamsi, hmm. Well, Mamsi, as you figure that out, I want to ask you a question. As a startup, you seem to have done very well, having these projects with Indian Oil and BHEL. So, how did you bring about this, these small strides of success for your startup?
Well, basically, we are a team. If I'm sending you a share document. Yes. 1 second, I'll show you for document. Okay, I will explain. And well, for telling about this startup story, we have, well, for the fuel cells, we are already there from 2012. Basically, we are doing some kind of material supply to many organizations in India, especially the IOCL, BHEL, VSSC. All these organizations, we have been supplying the fuel cell components of graphite materials. So in 2020, we started up a company in which we have done some level of groundwork before we've done a startup. So that is where we have applied for a IOCL project with a three-tier screening of IOCL. We have got the funding from IOCL for development LCV, light commercial vehicle. And also we have also got a funded project for a golf cart development also, which golf cart is not feasible for fuel cells. I agree, but the customer wants it, and we are doing the golf cart also. You are all invited to Hyderabad. Nishant sir, I already told you to come to Hyderabad whenever you are there. So we will do it. We don't really announce ourselves to a very big player, but of course we are doing a lot of work on the fuel cells.
No, that's very, very inspiring to hear, Vamsi. But I'll let you continue with the rest of your presentation before we begin a discussion. Well, Vamsi, it's completely fine though if you don't have a presentation.
No, we have a presentation today morning. I'm currently in Bhopal. I have done a presentation at just now to the Madhya Pradesh government. I will send you to your WhatsApp, please, if you don't mind. You can open it.
Sure, I can share it with the group. Yeah, no problem. Please do. Well, Santhosh, there were some interesting questions in the meantime. And there was one question that, a lot of them have asked me as well, but I never really, figured out how this could, be resolved. One is if you're going to put hydrogen into these fuel cells, how are you going to determine if it's green or gray, right? Someone's going to give me gray hydrogen from the middle of nowhere, and it's already inside my fuel cell. How will I know?
So I'll give the right answer and the not so right answer. So the first part is, as a fuel cell OEM, we don't care. I mean, because as long as the hydrogen quality is maintained, whether it is produced using methane pyrolysis or it's producing using coal or is produced using white hydrogen from the oil wells, I personally don't care, right? Because my fuel cell does not care. Now, obviously, and as we are selling the fuel cell, right? Similar to if you're selling a, let's say, genset, I mean, they don't know if the diesel is coming from oil produced. So whether diesel is coming from, let's say, oil produced out of Africa or from Russia, right? So I know that's not a very, let's say, nice answer, but then, but that's what it is, right? That's the fact. As an OEM, we cannot help it as well, legally speaking, because we provide the equipment and the company or the, let's say, the customer has to source the, let's say, hydrogen for themselves. However, what we are seeing in a number of these early stage projects, hydrogen production is co-located. I mean, for example, using electrolyzer, as told about this project in SJVN where it's a company called Aerox Nigeria. They installed an electrolyzer and it was powered by solar, and it only operates during the solar hours. So, so it is green hydrogen in that sense. And also, in order to get a lot of benefits and subsidies, unless you'll have to adhere to the green hydrogen definitions of local jurisdictions. In India, MNRE has come up with a definition which Bureau of Energy Efficiency is going to ratify. And similarly, there's a RED 2 in, let's say, Europe, and there is an IRA definition in US, etc., etc. Right? So, so that is there according to the law of the land, and whoever is installing it. From a perspective that they want a green electricity, right, and they're moving away from diesel gensets, then they'll have to use green hydrogen, and only then they're going to get the benefits, right, both on the green side as well as on the hydrogen side. So, so yeah, that's the softer answer to it, but yeah.
No, that's good. I mean, you're not the first, manufacturer to tell me this, and I wonder if Georgios or Professor Stylianos, you all have a perspective, but it's only from the pure viewpoint of sustainability that you're looking at the colors, right? But as an equipment manufacturer, you just want good quality hydrogen based on what you've developed.
I
Professor,
will
please.
agree with Santhosh that it doesn't matter where this hydrogen is coming from. When it comes to the point to be delivered into a network and be supplied to a fuel cell, certainly this hydrogen would have certain specifications. But in any case, it is like electricity that we are using today. We have electricity from coal, we have electricity from renewables, and they all enter into a network. In the case of hydrogen, certainly it is not a very easy thing to create a network and each and everywhere in a city to have the supply of hydrogen. Mainly, I see that in remote areas or in single houses, we may have, or where the grid is not very easily available, we may have the production of hydrogen on site. And this production of hydrogen on site has to be green. So it will be produced with green technologies and will be consumed also on site. But in any case, if the hydrogen is being delivered through a grid, I think it does not matter where it comes from, whether it is gray, it is blue, or it is green.
Got it.
Just one more thing which I'll add, right? And I think that's very important for people to know, right? So when, for example, I just give you an example, right? So if you are currently you're producing diesel, right? There is a scope 1, 2, 3 emission on the diesel, let's say, usage side. Now, let's say that you have a refinery use case where you use gray hydrogen instead of green hydrogen, and you produce diesel. It does not become green diesel. In fact, the cumulative emission just decreases by like 7% or 10% at max, right? Nothing more than that. But then if you're using but now you are replacing diesel genset with a fuel cell, right? Where let's say you're basically replacing the scope 1 emission in that sense of the diesel genset with fuel cell itself. You are decreasing it significantly. I mean, in the sense that it decreases to the tune of 75% or 80%. Even if you use gray hydrogen, that is decreased by 50 or 60%, right? So it is basically, it's not apple to apple comparison always. And let's say that you have to always use green for everything is also not realistic. I mean, none of us are doing it anyway, all for green electricity or even our EVs if we own one.
No, it's good. We need to do something to have these technologies scale and be adapted, right? Because we cannot have renewable energy power, address our energy needs anytime in the next decade or so. It's a long way to go. So completely agree. And I hope, whoever asked that question got their answer. We'll have Vamsi go through his presentation for the next 5 minutes, and then we'll spend another 5 minutes if there are any questions. But Vamsi, over to you.
You are seeing the slides, right? Are you seeing the slides?
We see it, Vamsi, please.
Okay, this is the outline that I am going to give you in the presentation. I will scroll it fast. Any questions if the audience have are free to ask me later on. So fuel cell components, stacks and systems. The importance of fuel cell technology as laid down by the other speaker. Problem statements and solutions, credentials of VG systems, current status, business opportunities and case studies. Discussions are moving forward in partnership. So needless to say, how the fuel cell works. So this is how the fuel cell components are laid down. The current plate, the current collector plate at the top, separator plate, the gaskets, the gas diffusion layers, how they are laid down, and finally it's the membrane electrode assembly which is sandwiched. So this is how the fuel cells transforms: cell to stack, stack to system. And this is all the components indigenously we developed. These are all from development fund. One of the premium quality of our company is that we did not invest 1 rupee. We are always dependent on the developmental projects, and we have developed the projects suiting to us and as well as the client. For example, BHL has given us a funding project for development of a gasket. We developed the gasket for ourselves and we indigenized the gasket, and we again sold the gaskets to BHL kind of thing. So we have special gaskets which we developed, and we also offers composite plates, bipolar plates, which are suitable for fuel cell or flow battery technology, which of course you can evaluate. You can come to our lab and see how the gaskets and bipolar plates will be there. And we are also developing a novel process to minimize the matching cost in the CNC, making the micro channels which are being used for the distributing of the gases. This will cut down the cost immensely for the time for the CNC and as well as the cost. Yes, this is schematic of the fuel cell system, how it looks like with the gas diffusion layers, humidifiers and other BMS materials. And of course, why fuel cells are important. System compaction, it is more silent. The cost competitiveness in heavy transport applications, we clearly say that the two-wheelers, the three-wheelers, and a very light commercial vehicles up to 1 ton battery is the best. And when it crosses that, then fuel cells for the buses and large LCVs, the fuel cells are the best. So refilling time is just like CNG, so no worries on this. And national perspective of hydrogen is already laid down by MNRE, and it is widely available. I just given an outline of this. This presentation I already shared it to Nishant sir, and Nishant sir can distribute to whomever concerned. So these are all the credentials. Means our manpower. I am the current CEO, and I'm a mechanical engineer. And we have 7 doctorates in our team. Dr. Shiva, who is a specialist in battery. A battery car or a battery things doesn't need a fuel cell, but a fuel cell always needs a battery. So we have a battery specialist, Dr. Shiva, and Dr. Hubert Mancher, one of the very renowned scientists in the integration, control engineering, and instrumentation. He is a very efficient control engineer and develops the softwares. Dr. Karki Middlestead is a very renowned fuel cell and electrolyzer specialist. Dr. Vamsi Krishna, he is a testing man in our, and Dr. Sumant, he is worked in Chevron for 35 years and he joined our company. Currently, Chevron, he is very good at hydrogen and safety and transportation. So Kushagra Yadav and composite materials. All of the team we have is 21 people. All are engineers, and the 7 doctorates we have and on our team. So what makes our fuel cell more efficient and this thing is, we make one statement I can give you, that we make our fuel cell, but we love our baby. But who has to vetify it? Who has to vet it? So some players are there who will come here and makes our fuel more redundant and robust. So this is the problem statement that everybody knows: the rise of oil prices, green to H2 availability, rise of lithium cells due to rise of EV demand. And the solution to use the fuel cells is using hydrogen as alternative green fuel, carbon neutral energy using fuel cells. One of the major project also we are doing for military. So this is a classified one. I do not wanted to elaborate more on this, but fuel cells are widely used in military and BrahMos missiles also. We are working on them, but they do not want to share with, and that's what we are not sharing. So the uniqueness of our startup, we are a TCO demonstration of LCV trucks for range of 350 kilometers. System developments we are doing with indigenous subsystems. We have a rich team as explained. Target products and services, fuel cell stacks for customized systems, fuel cell systems for vehicle integrators, hybrid energy kits for EV distributors, PEM fuel cell systems for non-transportation sectors like solar, and they're like telecom backup or ATM backup or generators. These are the business opportunities in non-transportation. Drone, I think one professor has already covered this topic of drone. I have also asked a question to him. Just to have a professor, please have a look at it. So this is about the business opportunities where we can penetrate into activity. And this is business opportunity transportation, forklifts, trucks, trains, airplanes, you name it. This is the LCV market potential. So we think that this is a slide taken from Statistica. The actual EV vehicles and domestic vehicles which are flying in the market, even if the potential of fuel cell goes into 2% or 3%, that itself is a game change. So this is a TCO case study, which we have done with the diesel, electricity, electrical, and the fuel cell. So if the fuel cell cost of a hydrogen comes at 250 rupees, then the cost of the fuel cell will be cost of the per kilometer will be 9.77 rupees. So this chart, please, is a calculation that we have done with the real figures. So Nishant sir, just have a look at it, and I request you to just keep to your own eyes. This is our certification of DPIT, and these are our customers, some of the customers, with their permission. Thank you very much for the opportunity. Please free to air your questions, please.
No, Vamsi, thanks for making that very quick as well, right? And I like how you had this, done very, in the most simple manner. But this is an open question to everybody, all our expert speakers who are here. It's where do you see, applications for PEM fuel cells? Let's not talk about high temperature PEM. I understand that it's a little bit more niche, but generally for fuel cells, where do you see the, applications taking off, in a large scale before any other segment or industry? Yes, Vamsi, go ahead.
See, already fuel cells for mobility applications, people are widely using in forklifts. That's already on the market. Plug Power has done an innumerable business at the forklifts. the easy to take off for the fuel cells at this moment. At this moment, I would say microgrid is the most important topic. Important topic of this is a real application, real commercial application, which our other friend is already doing this job. So, and of course, the placements of diesel gensets, strategic reasons, and of course, for this is the second biggest thing it will come, that diesel generators, fuel cell generators, if you are matching a little price, even if a 20% price hike also, it will kick off very immediately. And light commercial vehicles, just we will demonstrate this light commercial vehicle in 2025 January. So that will be because when we are saying, sir, I wanted to tell you modestly, for our system, we are R&D to commercial. We don't talk anything about R&D, science, or this thing. What we do, we are telling it very clearly. So when we are demonstrating a LCV to IOCL, we will be very clear on the pricing part. That is most important part, is the commercial. How do we commercialize it is the only thinking that we have. So we always keep that in mind. And when we demonstrate the systems or anything to any corporation, we will keep the pricing very low down. If it is more than 20% or 30% of diesel, it's okay.
Thanks, Vamshi, and I also like the fact that you have this approach to look at commercial viability from the very beginning, because I think that is one of the reasons why so many technologies today exist on paper and in the lab, but have never made it to large-scale commercial demonstration. And that's something as an organization we're trying to address. Santhosh, do you want to come in on this, or should I move to the next?
Yeah, I mean, let's hear from Georgios as well. Why not? And then we can always I can always add late to that. Vamsi, you can stop sharing your screen, or Nish, you can stop sharing Vamsi's screen.
Vamshi, can you just remove the screen off?
Yes.
Georgios, Professor Stylianos, do you have anything you saw in the chat that you want to respond to? Or yes, Georgios, please.
No, just a general comment about the applications of PEM fuel cells. Let's say I don't agree with a notion that high temperature PEM has a niche. It actually can perform in many applications better than low temperature PEM. Low temperature PEM are there because, let's say, the technology or the materials are more established at the moment and proven in their durability, namely Naphthalene and PFSA membranes. But I don't see a huge discrepancy on how the applications could be. Actually, high temperature PEM, especially for mobility applications, can be beneficial because they simplify the cooling of the fuel cell and the system in terms much more. So it needs smaller systems to operate. Let's move to the questions.
No, that was good. Thanks for clarifying that, Georgios. But on that point, there's also another question in the chat. I think it came from Rahul. From Rahul, it says, what percentage? Sorry, why is H2 fuel cell not viable for light vehicles? Sorry, I saw something else, but I thought I saw something else between low temperature and high temperature. But what is the cost difference, Georgios, between low temperature fuel cells and high temperature fuel cells? What's the percentage of cost?
I mean, I don't see a cost difference per se. What I mainly, I mean, you have a simplified balance of plant in terms of cooling. So if you imagine a fuel cell vehicle with a high temperature PEM fuel cell, you would operate on you would need a much smaller radiator to cool down, let's say, the engine or the fuel cell of the vehicle, right? So this kind of systems are smaller, lighter, and so on. The cost barrier, I mean, I don't see a difference. Let's say Naphthalene or PFSA membranes are more mass produced naturally than membranes that have been developed, or let's say PBI and so on. They've been around for longer, but their cost is much higher, and we should not forget that there are also perfluorinated membranes. So fluorine is something that is getting more strongly regulated, especially in Europe, more and more. And it is a kind of a question: when will be the time where we will completely ban it from any kind of carbon-containing structures? So let's say from any applications as lubricants or even membranes for fuel cells. So this is a question on many levels. It's not just a cost comparison. It's an environmental cost comparison. It's also sustainability comparison of how we move forward with all these things.
And okay,
Thanks for shedding light on that. Yes.
And to add on this, okay, if we talk on absolute terms, somebody can say that the high temperature PEM fuel cells, they are using higher loadings of platinum. But this is something that it has to do with the general balance of plant that you have to use the fuel cell. In many aspects, I see that the PEM technology, the low temperature PEM technology, it is quite mature. I think the car industry spent a lot of money to develop it. I think that in the small cars, it is the technology that will prevail. I do not think that the low temperature PEM fuel cell will be the technology for trucks, for example, because the engines and the power output they are needed is very large, and cooling is the main issue when we are discussing about trucks. So I think that the high temperature PEM fuel cells will have their role in this massive, large transportation of goods and all this kind of stuff.
It's great to know it's more sustainable as well, as Georgios mentioned. But Santhosh, over to you, Santhosh, if you have some comments from what was just spoken. And
yeah, I mean, I think what Georgios mentioned was absolutely right. I mean, PFAS is becoming a big issue. Fluorine. I mean, I used to work in let's say when I was at Shell, I used to be responsible for both the hydrogen plant as well as the hydrofluoric acid alkylation plant. So I can imagine, I know what HF is and what it takes to get it from that component to let's say membrane. So definitely, PFAS regulations will become more and more challenging, and we'll have to kind of look at non-PFAS free membranes or HT-PEM technology. So I do completely agree with both Professor and Georgios that HT-PEM is going to take up more and more chunk of some of the traditional LT-PEM use cases. And perhaps there will be a balance between the two, right? I mean, in the end of the day, looking at even CHP, remote places, HT-PEM is an amazing technology. Again, some time to go overall, but still, I believe HT-PEM would be there. And in addition to that, some of the use cases what you asked, Nish, I mean, personally, I have my, let's say, I wouldn't say concerns, but I have my apprehensions with regards to mobility use cases, specifically lighter mobility. Let it be LCVs or even two-wheelers or three-wheelers and four-wheelers. And the reason is not per se that hydrogen cannot be a solution there. I mean, of course, anything can be a solution, right? I mean, as long as you have the right infrastructure and the right policies towards it. But I think the reason being that the electric movement on those fronts have moved much faster, right? And the infrastructure has already been established much better, that the reason to create an all new infrastructure for hydrogen for these lighter equation vehicles in specifically geographies where electrification and electric mobility has already taken precedence doesn't make a lot of sense. I mean, at least for these lighter mobility vehicles. I mean, purely from why do you need to have a dual infrastructure for something which you already have a primary infrastructure? But then for a larger, it's a completely different discussion, right? Trucks and buses and planes and shipping and maritime, a completely different discussion. And there might be, let's say, definitely geographies where there is nothing on e-mobility front, right? There you can come with a complete new policy and choose to go one route or the other route, right? And it's not like, I mean, of course, there are these Michael Librish kind of graphs on, round trip efficiency and stuff like that. Of course, those things are true to a certain extent, but they're just half truth, right? I mean, eventually it's, what works for the country the best and what works in terms of overall infrastructure cost and import and export and everything. So there, hydrogen could definitely be a solution even for lighter mobility in certain geographies, but maybe not everywhere else.
Thanks, Santhosh. Vamshi, please, you have your hand up, and I think I was just going to call you
Well,
for some closing
yeah,
remarks.
just I have just a small thing to say. Every month, every year, two-wheelers and three-wheelers of EV, two-wheelers and three-wheelers, and even small LCV vehicles have already been sold in a very high number. Some 2 lakhs or 3 lakhs or so much number everybody is buying. So in the same time, one should understand the major concern of the oil industry is the denting of their business. They are already having their dent of their business. These two-wheelers buyers are not coming to the petrol bunks to get the diesel or petrol. Now already they are in biggest problems. So the point of infrastructure of electricity is already in the place. But what should the oil companies do? So their main business, or they are going alternative oil or gas. That is where the major interest will come for the.
Just one last remark, right? I mean, let's say the electric part of that business. I mean, whatever oil and gas companies are doing right now, there's so much of money they spend or they earn using oil and gas. There's a long way to go before they have to even think of that revenue getting dented. At least that's how the numbers say, and that's how, let's say, the profits of these companies say. So that's a completely different topic altogether. But I mean, I do see, Vamsi, I mean, there is a reason for that, but perhaps not because we need to get additional revenue source for an oil and gas company. I mean, but then perhaps something more, let's say, structural, that some geographies where electric penetration just doesn't make sense. Let's say Kerala, for example, right? I mean, there is no renewable energy, for example. So everything is electricity is completely imported, but there is water. Could you make green hydrogen? I don't know. Could you make green hydrogen out of waste and use that for mobility in that region? It's like micro community for mobility power. So similarly, Northeast, right? There's so much of bio-based sources. Why do you have to put up so much of difficult infrastructure, electricity cables? But yeah, I mean, but yeah, that's just my 2 cents. But overall, I believe that fuel cell in the longer run has two main applications. One is grid scale storage. Second is mobility side, which is both aviation and shipping. Right. So I think these two will be the bigger pieces, maybe 2, 3, 4, 5 years down the line, where the entire industry will kind of converge to. But that's just my prediction.
Thanks very much, Santosh. Every day I learn so much more about this entire value chain where, what we call green hydrogen today, right? And some parts of this value chain have been existent for decades. But going forward, I think the last question or that statement, it sums it up. My answer to you will sum it up perfectly. I've been, in the automobile industry for 20 years, and we've seen what EV has done. And there will not be a point where, when someone says stop oil, people will stop oil. No, it's not going to happen, right? We will see oil and gas and several other industries coexist with whatever is being developed. And it's only the ratios that will differ. And like Santosh pointed out, based on geographical factors, based on political factors, different countries and different communities will choose different technologies that are best suited to them. But today, as an organization like the Green Hydrogen Organization, we want to ensure whatever is being done to fight the climate crisis, we do it sustainably, right? Even though some of these manufacturers here don't agree. But that being said, I want to thank Professor Stylianos, Georgios, Santhosh, and Vamsi for taking out their time. And I'm surprised that so many of you all have stayed back until the very end. So I appreciate that as well. I see you all have a lot of questions. You can see this webinar again in 2 days' time on our YouTube channel. And if you were registered for the webinar, you will get a copy of the presentations that were shared by the speakers. So with that, thanks everyone for joining in. Unless, Professor, do you have something to say? You're on mute, Professor. Sorry. Professor, you're on mute.
Okay, it was a nice discussion. We have seen and discussed also with people from industry and other organizations. And it is true that we have to keep in mind that, in the case of the renewables, the photovoltaics or the wind turbines, they spend
కంపెనీలు డబ్బులు ఎంత టెంట్ అయినా వాళ్ళకు ఉన్న బిజినెస్ స్కేల్స్ లో నథింగ్ అంటున్నాడు.
Sorry.
They spend much more money than they have already spent for the fuel cells to come into market. So I think that it's a matter of a capital investment to see the fuel cells to be spread and become part of our lives. It's a capital investment, it's a political decision, because already we see the catastrophes that we have from the climate change and all these issues that brought the very sharp development that we had within the 20th century. It may be the very beginning of the 21st century. I think that the sustainability of energy, it goes through the renewables, and the renewables to be used, they need certain tools, and these tools are batteries and fuel cells and electrolyzers. That's all.
Thank you very much, Professor. And with those remarks, I will end this webinar. And if you all have any other questions or queries, please feel free to reach out to us through our email channels or LinkedIn. And if Professor is okay, I will share his emails and Santhosh's email to everybody. So thanks, everyone. Goodbye.
Bye-bye.